Yeah, go ahead, Scott. The floor is yours.
Okay. Well, this is going to be very ad lib. I don't have a. I mean, I do have a little PowerPoint, but it's going to be. And actually, Jeff and Steve, you guys, I think, will be most interested in this because this is all about home brewing and getting started with a home brew. And I just want to back up in light of what Annalise said about modern radio and the idea of software defined radio and things like that. I'm totally on board with all that stuff because I used to do a lot of DSP, not really DSP work, but a lot of programming for making boxcar filters and all sorts of things that clean up mostly visual images that I was able to gather during my time as a graduate student and beyond that a little bit, with special homebrew laboratory equipment that was able to, actually look at molecules and atomic things with atomic resolution, and it was done in a very interesting way. But a lot of the software we had to work with, we had to make at that time our own basic filtering video filtering software. So I was doing a lot of that. So I'm very much aware of that kind of software, what it can do, and I'm into DSP and all that. But in the end, the signal, if you're making a transmitter of any kind, and you're going to need some analog pieces as well. I guess the same thing applies to receivers, but you do need, in the end, an analog final amplifier. So, and that's great. So that's kind of where I'm going to start here. So it started out where on Saturday at Rick Real, I was able to go by the table when you first walk in. You have the guy. They have that. They're always there every year. They have a couple of tables that are strung out, and it takes up the entire entrance to the building that the ham fair is going on in. And his name is Hammerschlag, I think, or something like that. And he always sells a lot of parts. You can find all kinds of different connectors with him, and tools and chassis and enclosures, and but also he's even got vacuum tubes. And I was walking by the table, one of his tables, and I happened to notice. Let me see, this thing, and it's a 1200 volt. It's a plate transformer. Puts out 1250 volts at 200 milliamps. It's for those of you who would know this or understand it, it's 235 volt amps. Reactive power kind of potential there. So I asked him, I said, well, how much do you want for this? And he said, oh, $25. And I'm like looking at him like, what? Because I know these things go for at least a couple $100. I mean, it's it's brand new. It's never been used. It's like, and he wanted $25 for it. So I said, okay, I'll take it. And so the reason why I took it was because I've always wanted to build or convert. Let me show you this thing. This crazy thing. I don't know if you guys can see it well. This was something I picked up several years ago at a store in Hillsborough called Surplus Gizmos. Has anybody ever heard of Surplus Gizmos?
Oh, yes.
Okay, so they have all kinds of crazy stuff, and I was looking at their test equipment that they were selling. They sell lots of oscilloscopes and spectrum analyzers and all that. And this thing was sitting there. This one day I was there, and I looked at it. I said, "This thing looks like a ham radio thing." And I looked at it closer, and sure enough, it is. And it was somebody's ham radio. They were selling it for $25.
No.
Yeah. So
Oh,
here's the back of it. I mean,
the knobs are worth that.
I know. So it's
Holy
got these.
crap.
Actually, those are not. Those are 807 tubes. The two big ones on the right, and it's got a driver 6Y. I can't remember the. Anyway, it's like got. I mean, it's just like talk about homebrew. You can see the coils there, and you can see maybe a few other parts. This was completely homebrewed by somebody, God knows how many years ago, and
Yeah.
probably they passed away, and their families, gave it away or sold it, and somehow it ended up at surplus gizmos, and they were just giving it away for $25. In fact, I think I got the price tag on this thing still. You can
Oh,
probably see it like $27 and whatever 50 cents there they were selling it for. because they had no idea what. And then well, the guy put whoever. I don't know if you can read that, or is it backwards?
No.
Yeah, you can see what they were saying about this thing there. So it's saying what kind of parts are in there and so forth. And so it was a steal, basically. I figured if nothing else, I would use it for parts, and I would build a, amplifier with this thing one of these days. But my biggest limitation was, the power supply, and because I knew I would have to buy a fairly expensive transformer, to start off with. So when I decided I would do a linear power supply. And I toyed with the idea of a switching power supply and all that, which still can be done. But when I saw this for $25, I said, I'll do it. Okay, so then the question was, okay, now that I got, that basis, what can I, how do I design the first thing I need to do is build a power supply so I can, power these tubes, because as everybody knows, vacuum tubes need a lot of voltage. And so it's not a trivial pursuit to build a power supply for this thing. So I went through the process of really, and especially I think, well, Steve, you say you did a homebrew amplifier, but it's transistor, but it's still the same thing. The idea is it is homebrewed. And then of course Jeff, he does nothing but homebrew. So you may have some very good insight for me on this thing. So let me go ahead and share my screen. I'll jump into my presentation. And let's see. Yeah, okay. So let's see if I can. Yeah, there we go. Okay, so the idea is that, this is something that's not complete. I was going to use it partially as just kind of like my journey in how do you design a power supply to accommodate the tubes that are, I'm choosing to use the final amplifier tubes and other things as well. And then I was hoping that this would be an instructional as well as kind of a journey kind of presentation. I'm not sure what it is going to be. I think it's more journey than instructional, but I can use some help along the way here. So let's go ahead and launch into what's going on. Okay, so first off, we've got this situation for the final tubes. This is just a very simplified diagram showing you the basic schematic. And of course, what I've got here are these are RC811 triode tubes, which are the main power tubes. And they are driven by this driver here, of which I was starting to write down the tube, designation. And it is actually, hang on one second. Where is it here? I pulled it out of the thing so I can see what the number is on it. And it's one of those things where it's kind of faded and it's hard to find it.
6Y6?
What's that?
6Y6?
No, it's got 4 characters.
Okay.
I'm just trying to find the darn thing. But anyway, okay, I won't waste your time with that. But anyway, well, I'll eventually I will eventually find it. Because there's no schematic, of course, for this. It's just you have to look at the circuit and try to figure out. And you don't have to go. The beauty of it is I can just do anything I want. I can. What I'm showing here is the tubes are in parallel, or they're parallel together, and so you can get each tube can you can combine the current from each tube and you sort of double the amount of power that you can get out of any one tube. Maybe not quite double it, but almost double it. In any case, and then that current coming out of the plates here. By the way, does everybody know when you look at a schematic for a vacuum tube, what you're looking at? Because I'm not sure if everybody's familiar with tubes or tube diagrams. So I'll just name these things. Up here, by the way, you can see my cursor as well.
I grew up on tubes, Scott.
Okay. But we have a lot of people on tonight, and some of them may not know anything about. I mean, they don't even really know much about transistors, probably either. But
right.
But actually, tubes are fairly simple. They're actually simpler, I think, in some ways than transistors. But first off, can you see my cursor?
Yeah.
Okay, good. Okay, so these are the okay. So the idea is that you're conducting through the tube. From this here's the cathode, and you heat the cathode up, and it starts emitting electrons, kind of like a filament in a light bulb. But the electrons are attracted to the plate. The plate has a big positive voltage on that plate, and that's up here. And it doesn't literally look like a plate. It might be a cylinder that's wrapped around a filament, which could be a wire or something like a wire, or or a very tiny tube inside of a bigger tube, and the bigger tube could be the plate. And in the middle, you've got this thing called a grid in this case, which kind of like what the grid does. Okay, first off, you get current flow from the cathode to the plate. So the tube, you're actually conducting electrons through the vacuum of the tube. And so you have to put a very large voltage on these plates here in comparison to the cathode in order to attract the electrons and create an electric field to drive so the electrons will want to go to the plate. They're negatively charged and they're attracted to some very big positive object, and that would be the plate. And so that happens, and then you regulate the flow by putting a voltage on this grid. And the reason why it looks like it's kind of a dash thing is because electrons, it's a metallic object, but it's got, think of a screen, like a very, very fine mesh screen. And that's sort of what a grid is. And then electrons can actually get in between the wires of the mesh and fly out toward the plate and make it to the plate. And they get collected at the plate and then flow into the wires, and then usually go through some sort of a load. So I'm representing that by this, what I'm calling a plate resistor over here. But the grid is regulating that flow. A lot of times what we can do is we can put a voltage on the grid of AC voltage on the grid, and the AC voltage will cause the current, the electron current that's flowing in the vacuum to sort of modulate itself too in a sinusoidal fashion. So, you're increasing and then decreasing and increasing and decreasing. So then eventually what's happening, you're getting a sinusoidal current that's being collected on the plate, and you get the sinusoidal current that's flowing and that's wired to the resistor. And the current flows through the resistor. And as we know, when a current flows through the resistor, we get a voltage drop. Okay. So there's a voltage drop occurring sinusoidally on the resistor here. And then to make things more complex, you can get, if you're modulating with a voice, you have many different sine waves, correct, that are simultaneously happening all at the same time. And then so you're getting this very complex waveform that's showing up as a complex waveform voltage across this resistor. And down here, I have something called B plus, which really means the voltage supply or the power supply for the plate, that's supplying the plates here. So we're talking about, putting maybe several hundred volts up here to maybe even a couple of thousand volts. And then, the voltage, there could be a voltage on the grids, which is like what we call a bias voltage. It could be anywhere from something like maybe minus 10 volts to minus a couple of hundred volts. And then that's DC voltage. And then the AC voltage is superimposed on that. So then the voltage on the grid is say pinned down at minus 40 volts or something like that. And then you might have a voltage that's going up and down. The signal voltage is a sinusoidal voltage, which is going up and down, maybe plus minus 10 volts, or who knows. I'm just making these numbers up. So then the voltage varies from say minus 30 to minus 50 sinusoidally at the frequency of whatever, what the signal is. In this case, it could be a voice signal or it could be an RF signal. So you could be pumping in here, say 14 megahertz. And so you're getting this variation of the grid voltage at 14 megahertz. So it could be anything from audio frequencies up to, pretty high radio frequencies and so forth. So anyway, that's the idea. So the amplifier is and the idea is that these tubes would be used as the final amplifier tubes in this particular case, and they would be pumping out, each one may be able to generate 100 watts. And so you combine them together, you might get 200 watts coming out. And then our plate over here is, well, it's not really a resistor, but let's just say it is. And then it's acting, whatever the load is over here is acting as a resistor. Okay. So then the thing is, and oh, by the way, over here, you've got the driver, which I'm still trying to figure out what the full name is for it. We'll get there. Anyway, that's supplying. This is a pentode in this case. You've got five electrodes. You've got the plate. You've got a cathode, and you've got a grid. What we call in this case called the control grid. And there are two other grids, and one's called the screen grid. The other is a suppressor grid. And the screen grid needs a voltage on it. But anyway, I won't go into those details. But anyway, just suffice it to say that the driver is supplying whatever voltage is necessary to go to these grids here to do, to make these tubes work the way you want them to. Okay. And anyway, so based on that, and based on the fact that, okay, I'm naming these tubes as RCA 811 tubes. How do we go about designing? Okay, starting off with a power supply to be able to supply the voltages required to these tubes. So that's where the journey begins, I would say. You could also connect these tubes up together and as a push-pull system, which I won't get into. And there's ways, but a lot of times people just go ahead and parallel these together, and then you can extract currents, a current from one, a current from the other, and they're identical, and they add up, and that way you can sort of double the amount of power you'll be able to get out eventually to the antenna. Okay, so yeah, so the idea is that what you're concerned about is how much voltage can you put on the plate of these things without damaging, without causing any damage, and so that's where we have to know how much voltage we can get out of our power supply. That's to start with. And then we know that the voltage on the plate is going to be this voltage here. I have this little equation up here, VV plus minus the current that comes, when I say IB here, I'm talking about the plate. Okay, that's current coming out of the plate. That would be this instantaneous sinusoidal current going through the resistor. So that's IB times our plate would be the voltage drop across this resistor, which is varying in time, at least sinusoidally, but usually much more complex than that. It's a complex waveform in a lot of cases. And you got RF, and you could have audio on it if it's a voice signal, or it could be a CW signal. It's just pure RF, that kind of thing. And so anyway, so the plate voltage is going to be varying. Going up and down. This component here is going to be the sinusoidal part, okay? Whereas this VB plus is going to be the DC voltage that this part here, the voltage drop across the resistor, is superimposed upon. So the maximum voltage, if IB is 0, and that can happen, then the maximum voltage would be the voltage of the power supply. And then the minimum voltage would be some maximum current here times it. And the resistor, of course, doesn't change, but that would determine what we call the voltage swing on these plates. All right, so let me move on to the next slide if I can. So anyway, the first thing you have to learn is that whether you're dealing with transistors or tubes in the analog world, that there are characteristics that are involved with the tube or the transistor. So I chose the characteristic. This here is a current voltage curve for the 811 tube that you just saw in schematic form anyway. And so what you see here are a bunch of family of curves that are taken where the grid voltage is biased at a certain voltage. And then what they do is they run the plate voltage, they vary the plate voltage. And this is all DC. This is without applying, any kind of a signal to it. So in other words, going back to this graph, we just bias, we put a DC voltage on the grid. We don't put any AC component there. And all we're doing is we're changing B plus over here. Okay. And maybe we don't even really have this resistor here. So, so these curves are taken from that scenario where you say put a particular voltage on the grid, and then you run you sweep the plate voltage, and then you measure the current. Okay, so the current's plotted on the vertical axis, the plate voltage is on the horizontal axis, and then you get this family of curves at different grid biases. Okay, so the more positive the grid bias, as you can see here, you start way down here at the 0 grid bias, and then they go plus 10 volts, plus 20 volts, plus 40 volts, and they go all the way up to 120 volts plus 120 volts, and they get this family of curves. So what you see here, first of all, is that at very small plate voltages, the current goes up pretty rapidly, but then it quickly kind of tapers off, and it plateaus in a way, and it rises much more slowly once you get past a certain amount of plate voltage. So what it's showing is, you won't get much more plate current for at a particular grid bias, if you really ramp up the plate voltage. And so anyway, but that's just the characteristic curve. But you use this a graph like this to actually design your system. At least you can get what the types of plate currents you're going to expect and the types of plate voltages you're going to expect to see when you actually operate the tube. And that's kind of where we're going here. So does anybody have any questions so far? I feel like I'm teaching a class. Jeff, does this make sense to you so far?
Yeah. Oh, it's making complete sense. And just for clarification, this plot you're showing, if you just change some of the names, most engineers would say, well, we're looking at an NPN transistor.
Yeah, transistors have a very similar, if you look at the family
Nearly
of curves,
identical.
yeah, what they do there for transistor, they would vary they would bias the base at different base
Currents.
voltages,
Yeah.
correct? Or
Yep,
currents,
yeah,
actually, right?
Yeah, it would be base currents instead of grid volts.
Right, exactly. So
And
because bipolar junction transistors would take, it's actually a current control device.
right.
So they would have these different currents at maybe microamp levels, and then you would see the amount of current flowing through the transistor from the collector down to the emitter, and that would be plotted on the vertical axis here, similar to the plate current, which is the current that flows through the tube in this case. But going to the transistor would be the current through the transistor, and then this voltage here would be the current, the collector emitter voltage. So that would be varied in a very similar way, and they would get these curves that would look almost identical.
Yeah.
So you're right.
And this also parallels identically to enhancement mode MOSFETs. The classic IRF 510 that gets so used. This is the exact same plot. It's just that instead of grid volts, it would be gate voltage. Instead of plate volts, it would be drain volts and drain current for the vertical, but will look very close to this.
Yeah, again, the field effect transistor he's talking about is, and I think that's is that a MOSFET or a JFET? The one you just mentioned.
The MOSFETs, but also there are some JFETs that are what we call enhancement mode, where you have to get positive gate voltage to turn it on. Most of the FETs that we grew up with, you had to put a negative voltage on the gate to turn the dumb things off. They were naturally all the way on.
On all the time. That's right.
Yeah, and you had to try to turn them off. But
right.
on your other schematic, as it relates to this, that load resistor you're showing, so typically in the amplifier context, that would be the resistance that the plates will see when they look back into the pi network that transforms from the 50 ohm antenna up to some higher resistance.
Yes, exactly. So I didn't want to get into the pi network, but yes. So basically, what you happen, I think the big thing we can mention is that this plate resistance is pretty high. I mean, we're talking usually thousands of ohms.
Yep.
And the plate, because the plate has where the tube has sort of a internal resistance. It depends on how much voltage you put on this plate and how much current's flowing through it, and that determines that resistance. And that's thousands of ohms. So you're matching that the output impedance of this tube,
right?
Its resistance. Is that right, Jeff?
Yep.
Okay. Yeah. So the idea is, and then the pi network that I think a lot of people have seen will transform those thousands of ohms to 50 ohms, which is what we want for the output of the transmitter going to the antenna. So that's what the job of the typical pi network. But the pi network will look like a resistor at resonance anyway to the tube.
Yeah.
So when you tune I think a lot of people are kind of at least have heard of the idea that when these old-fashioned tube transmitters, you have two knobs you have to turn it to tune it. We don't have to do that anymore with the transistor transmitters. They don't require that, but tubes did because they have such a huge output impedance that we required the pi network to be able to transform that, thousands of ohms down to 50 ohms. So, you can get the power out to the antenna. And so there were usually two capacitors involved, and one was the plate capacitor, and the other was the tuning capacitor. So the plate capacitor was the input capacitor to the pi network, and then that side of the pi network looked like, you wanted it to look like a few thousand ohms to match this output impedance of the tube. And then so then the tube would be happy, and you would tune this thing around so you get the proper match. But basically, when you got that proper match, that pi network, which is something similar to a parallel LC network, would be at resonance, and so it would look like a big resistor, to the tube. The tube didn't know any different. So anyway, I think that's the base. That's a very simple explanation of that, but I didn't go into any of that stuff yet. We'll do a part 2 on this when I get more advanced. Anyway, so going back to this graph, so you can use the graph actually to actually engineer or partially engineer this thing. And so I went through this book. Let's see. I have, let's see, hang on one second. So let me see here. I have so much stuff. Okay, so yeah, so excuse me one second. Let me just make sure I got the right thing. Okay, that's that. Yeah, so, oh dang, wait. Where's my, here we go. So this is the 1956, hang on one second. This is from 1956. This is, okay, I have books and books and books. I finally,
Wow.
So the only place I really found the proper information to be able to to try to design this thing was in here. RCA transmitting tubes from 1956. And somebody had photocopied this and made it into a PDF file and put it online. So that's where I'm getting this info from. So they have a design, a step of, first of all, you talk about, this is a general, you can see up here, Class C telegraphy service, multi-grid tubes, and then they got one here for triodes. Class C telegraphy service for triodes. Because remember, my tubes are triodes. So they tell you how to, step by step, do these little simple calculations to design the thing for whatever you've got. Okay, so I'm starting out, let me jump back to this. This here is a 1500, let's say, okay, my transformer, I think maximum voltage is 1500 volts. They tell you that. But actually, I think you can make it work a little bit more intelligently. It's 1250 volts, but I can probably get 1500 volts out of the secondary. Isn't that true? Jeff, have you had to do this kind of thing before? Hello?
Scott, you shouldn't be running your tubes at the maximum limit for high voltage. That could shorten the life because your tubes are going to probably be kind of old, and that would shorten the lives a fair amount. Just saying.
Okay. Well, I'm okay. That's the stuff I'd like to hear from you guys. But what I was going to do is I was going to say, okay, look, this is the recommendation that the book that I just showed you was giving. So this is like the process you would have to go through to figure this stuff out if you were to do it. But you're right, Steve. I think that running them, close to the limit is a little bit tricky. So I just want to say here, like this would be from the spec sheet. Actually, this is out of the book itself, but they go through all the, they have the book's all about showing you the specs for all these tubes. And so here it is for the for the 811. Okay, so I highlighted down here, the particular values of things that you really need to think about. So first of all, it's the plate voltage. They tell you these are maximum ratings. So as Steve was saying, if I say I wanted to work at 1500 volts, that's like the maximum rating I should go to. But what I was trying to get at, and I think Steve picked that up, was actually I can go higher because what I was going to say was if I'm operating or wanting to operate as a Class C amplifier, and I know I'm probably going over the heads of a lot of people here. Class C means that that this tube is conducting only a portion of the cycle. You think of a sine wave, its cycle is 360 degrees, correct? To jog your memory, if you don't think about these kinds of things too often. We have different classes of amplifiers. There's Class A, Class B, Class C, and there's even Class D and Class C and so forth. But Class A through Class C are the more conventional ones. Class A, you're amplifying or you're sending through the full 360 degrees of the sine wave is being amplified. Okay, so the tube has to be conducting through the entire RF cycle. Every RF cycle that goes through there, it's conducting. So as a result, it's not as efficient as something that may conduct a smaller portion of the RF cycle. So you can work the voltages on this tube, so it will only activate only for a portion of the cycle. For instance, Class A is on all the time, and it's amplifying throughout the entire RF cycle. Class B, you're only amplifying through half the RF cycle, 180 degrees of that 360 is being amplified. So say if you think of a sine wave, just say the positive portion or the negative portion of the sine wave is actually being amplified. Or the tube is conducting during only half that portion. For Class C, it's less than 180 degrees. So what they said was, at least the wisdom at the time was, yeah, you can, if you really want to push it to higher voltages than what they're telling you here, if you run Class C, you probably could. However, you could probably go higher in voltage because you're only conducting a portion of the time. And not only that, but if you're doing CW, you're actually having the tube work for not 100% of the time. It's only like when you key down on that key, it's going to amplify, but when you key up on the key, it's not amplifying. So there's a period of time where the tube has a chance to cool off. Okay, because the main problem is you don't want the tube to overheat, and that's what they're kind of concerned about. And plus, the voltage stress that may be happening on the electrodes, the internal electrodes, due to very high voltages, may be an issue as well, which can shorten the life of the tube. So I guess the conventional wisdom would be operate your tube at a lower voltage, and you'll notice that the voltages the columns have different values here. The CCS and the ICAS. So what do those mean? Well, CCS is continuous commercial service, meaning, like, for instance, if you use this tube, I think what they mean by commercial service would be something like a commercial radio station, perhaps. Maybe there's other uses where the tube is on constantly. It's never turned off, and it's just constantly being used. And many times, it's used 100% of the time. It could be used for Class A. It would definitely be used for Class A amplification, or maybe it could be used for also if it's an FM radio station, like they say FM telephony here. Then it could be a Class C amplifier too, because you don't need to have. For reasons I won't get into, the tube does not have to be conducting, even 100 or half the time. It could be less than half the time to work FM. But for AM, it would have to be on all the time. Anyway, ICAS is, I think, intermittent commercial and amateur service. Is that correct? You correct me if I'm wrong, anybody. So this is where these numbers can go a little bit higher because now the tube is not being used all the time. It's intermittent. So and typically in ham radio and amateur radio, that's how many people use their equipment. It's not something that's on 24 hours a day constantly. So therefore, it could withstand a little bit higher types of voltages. So I'm just trying to point that out. And the main thing is what they're trying to show here is how much, what kind of input can you give it? So you can give it say maximum value 1500 volts 175 milliamps here would be the plate current. That'd be the maximum. And then one big, very important number to be concerned about is down here. First of all, the plate dissipation is 45 watts. What does that mean? Or 65 watts max. What does plate dissipation mean? It means how much heat the plate is giving off. Because remember, this, you're sending a current through this tube. The current's being collected on this little piece of metal, and it's not. And you can see here the current maximum is 175 milliamps, or 260 milliamps. Oh, sorry, 175 milliamps over here. So that's considerable amount of current. So eventually you're going to heat up your the tube will heat up, and you don't want the amount of heat that's coming off this tube. That would be say the watts, 45 watts or 65 watts. Plate dissipation would be essentially the amount of heat in watts that's coming off that tube. So you don't want that to be exceeded. So your power that you can get, if I say plate input here, 175 watts or 260 watts as the maximum plating current, plate input in terms of the power that goes into the tube is effectively. So what does that plate power input power mean? That's the plate voltage, say 1500 volts, times the maximum plate current, which in this case is 175 milliamps. If you do the math, it should come out to, say, over on this side, 260 watts. I'm sorry, 65. Yeah, 260 watts, right? Or 175 watts if it's in the CCS column. And of all that power that goes in as the DC power to actually have the tube operate, it's dissipating heat. So it's dissipating in CCS mode. It's dissipating maximum 45 watts. So let's say you run it over here in ICAS mode. There's 260 watt maximum, and you're going to dissipate maximum 65 watts is heat. Therefore, you subtract the 65 from the 260, you should get like 195 watts or thereabouts. That is actually could be used as useful power. In other words, the power that can go out to the antenna.
Yep.
Right. So
Yep.
Okay, now these are the maximum values. So that's pushing the tube. So you probably want to operate less than that to if you want the tube to last for a long time. So it all depends. And I'm a complete newcomer at this stuff, but this is the kinds of things I'm just going through the journey of how do you where do you get started? How do you start out calculating the values you're going to need? And by the way, is my transformer that I paid $25 for, is that going to do the job? And actually, it kind of looks like it may not, but anyway, it's a good start. So,
but the thing is, Scott, though, is even if you fired this thing up and only got yourself 50 to 75 watts out of it, which is not what you were hoping for, but that's still plenty of signal.
Yes.
So it's not something that anybody should ever consider a failure on something like this. And plenty of guys on the air do. If they get 950 watts out of their kilowatt, something's wrong in their minds.
Yeah, I understand.
It's nonsense. But
well, I understand. It's one thing, because the hope is, well, all my rigs can do 100 watts, so why can't I?
Right.
Why shouldn't I build something that can go higher? And so, right.
So I think the limiting thing here is how much current at that voltage can you get out of that transformer? That's going to probably be the limiting piece in this whole project, and it's probably going to be a bit less than what these tubes are capable of doing.
Okay, right. So let me move on. So we won't take up a lot more time. Let me move on to now. Okay, now that I know this information, okay, how do I build a power supply that can handle this? Okay, so first off, and we'll get into the voltage calculation. So first off, let me just go over basics of power supplies here. So we, I think everybody knows you have a transformer, and we're talking linear supplies. This has really not much to do with switching supply, so we won't get into that. This would be the old school linear supply where you have a transformer which will take your AC line voltage, convert that to, in this case, a much higher voltage, and then be able to rectify that, and then we'll get into the filtering part. So here, we got our transformer on the left. We got our diodes here, which will be the rectifying portion here on the right. And there's two ways we can do it. I'm talking about here full wave rectification, meaning that the well, halfway would be like, say we have one diode and forget about this other diode, and so whenever this diode is positive, so when you remember your sine wave goes up and down, it goes first positive peak and then negative peak and coming back. So say that imagine your sine wave here, and the sine wave. So what happens is on the secondary of the transformer, this is alternating. The voltage is alternating. I should say the voltage polarity is going up and down. So at first it's positive on the top, then negative on the bottom, then negative on the top, positive on the bottom, and it goes back and forth sinusoidally at the frequency 60 hertz here in this case. And then when you got the positive peak of the positive portion of the sine wave on the top of the coil here, then this diode here is forward biased. So it will conduct, and then it will only conduct. So imagine that the second diode is not there. So it only conducts for half the sine wave. Okay. And so imagine if that's the case, it's a half-wave rectifier. You would get see a positive peak of the sine wave popping out here. This graph here represents the output, the waveform of the output of this portion of the power supply. So you would get a peak, like a pulse, and then nothing, and then another pulse, a full cycle later. So if it's 60 hertz, I think what is it, 16 milliseconds per full cycle?
16.
So yeah, so every 16, I guess 16, I guess every 16 milliseconds you would get a pulse.
Yeah, you'll get half of a sine wave out of that top diode.
Right, exactly, just the first half. So a full wave rectifier is where now you include this other diode. So now, because remember I said that the voltage is flopping back and forth. I mean, I should say the polarity is going flopping back and forth. So now at the other half cycle, the top portion of the coil is negative, the bottom portion is positive. So now that will cause this diode to conduct. So the top diode conducts the positive portion of the sine wave, and then the other one is conducting at the negative portion, or I should say, when the voltage flops over to making the bottom of the coil positive, then this diode will conduct. And then you combine those outputs together, and now your waveform looks like, what you're seeing here, where you're getting a pulse every two pulses per cycle, or every approximately 8 milliseconds apart. Okay, so now that's your pulsating DC, the raw DC that's coming out of the rectifier section, and then that's great. And you can do that either with this, configuration, or what we'll call topology, or you can do it with a bridge configuration where you're using now 4 diodes in a bridge format or topology, and now you're getting exactly the same thing, but there's some advantages to using a bridge versus using the 2 diodes here. I don't think the advantages are particularly significant, unless Steve or Jeff have a comment about that. But anyway, the idea is that you're getting this pulsating DC, and now the thing is you want to get DC that looks much flatter than that. In other words, DC that doesn't really vary. It's just going from 0 volts to some positive voltage, and it's usually the peak voltage of your line voltage, or whatever the the RMS value of your secondary is here. So let's say in my case, I have for my transformer that I got for $25, it's supposed to be, I think, 1250 volts RMS, and to get the peak voltage out of this thing, isn't it 1.4 times that at the peak?
Yes, it will be square root of 2 times that RMS.
Yeah, exactly.
And
so
sometimes this is a big bonus. Sometimes
right.
you get something for a free lunch out of this in some power supply situations, but there's others where, oh crap, it's way too high. So it goes
yes, and I was dealing with that possibility too, that it would be too much.
Yep.
You have to deal with that. So okay, so based on that, I was and you guys, this is very going to be very sketchy here, but I'm going to go through it anyway. So after the, let me just say, after this rectifiers section here, let's say after this bridge, the bridge rectifier that you see here, and then it says to filter, and you got and now you get plus and minus. Now you've got kind of got this pulsating DC, but it's not AC anymore because AC goes negative, and now we're not going negative anymore. We're going from 0 up to this, positive voltage. So now you have to filter that to get rid of this wildly varying voltage. You want to make it flat. So there's a couple ways to do that. So generally, you put these filters, one of these types of filter designs, after that rectifying, portion of the circuit, and this filter should be able to take out all those pulses and smooth them out. Okay, and unfortunately, I didn't get a picture of what what the filters do, but basically, you've got again sort of a pi network going here in this case, and you don't need to have it like this, but we have two types of filters that I think are commonly used. I don't know if they're used so much anymore. We've got what they call a capacitive input filter and then an inductive input filter. And the capacitive input filter means that you've got a capacitor in front, then you've got some sort of an inductor or what we call a choke that follows that, and then we've got another capacitor that is in shunt. These capacitors are what we call in shunt because they're sort of orthogonal to the flow of the current here. And then you've got your this resistor here is I guess a bleeder resistor, and then you've got your your smooth output, which really looks like those pulses. What happens is it's going to be not 100% flatline DC, but it will have sort of a ripple to it. And then so imagine instead of having those pulses like we show here, just the tops of the pulses that are kind of connected together. And the better your filter is, the less wavy it will look. Yep. Okay, the wavy part of it is what we call ripple. And what we want to do is we want to reduce the ripples as much as possible. But that's kind of a secondary aspect that comes in with the choice of these capacitor values and maybe the choke value and things like that.
Oh yeah, very dependent. I mean, typical for this application. I mean, a typical inductor, there might be a Henry.
Yeah, it's pretty big.
It's not millihenries.
Oh yeah.
You gotta have a big reactance down at 60 hertz. So it winds up being pretty big capacitor values and a pretty big inductance value.
Yes, definitely. So yeah, and again, I would have to do a part 2 on this to really get into more of the actual design. But here's some stuff I found. Now, book-wise, to find this information, I had to search through a lot. I have a lot of books here. I have a big library of books that date way back into the 70s and beyond. And what I found was, I mean, I've got the radio handbook by a guy named William Orr, which I think the more maybe Jeff, Steve, you guys might know this particular book. And he's got very, very good information, but I couldn't find that in there. So to make a very long story short, I have a 1984 Radio Amateur's Handbook. I have my Radio Amateur Handbook collection is the newest one is 2018, and in that book they have a chapter on power supplies, but there's hardly any useful information in it. It's just basically will give you, how a power supply works, but it won't tell you how to design one. Okay.
Right.
And so it's very frustrating when you really want to get into it. So I had to get this, I dug up my 84, I don't know if you can see it, 1984 handbook. And so, finally in there, I found all this stuff. And they do go through the what you need to do to actually do this. So if you want to know, like, I'll stop the presentation pretty much here. But, this is an example of a design set of or a family of curves that are needed for the design of your output voltage from the filter. Okay, so what this is telling you is that, this is an example here. This has got nothing to do with what I've got going, but I didn't have time to really do the calculation for myself, but I'm just going to give it to you from the example in the book. just to give you an idea how it works. So what they do is they say, all right, they have, they're referring to this figure 8 here, which is what I pasted that portion of the figure 8 that was relevant on the right here. And so it's a family of curves, and they're kind of it's a weird, non, derived value kind of a thing that they're using for the values on the axes. Anyway, so their example is you got a transformer that has an output, say on the secondary of 350 volts RMS. You're feeding a load resistance. So here's your schematic. Here's your transformer. You got 350 volts RMS on the secondary. Your I think this is supposed to be the load resistor here, R. That's 2,000 ohms. There's a series resistance, which is up here. I think that's probably the resistance of the winding itself. But anyway, it's 200 ohms. And then the input capacitance to the filter section, which is just show one capacitor here, that's 20 microfarads. Okay. And then they say, okay, based on that, what is going to be your expected output voltage from the the final voltage coming out of the power supply, basically. So they say they give you the calculations you need to do. So you need to first take the R value, I guess load resistor, divide that by the no, it looks opposite though. The series resistor divided by what looks like to me like the load resistor, although they got that kind of backwards there. And so it's 200 divided by 2,000, which gives you the value of 0.1. And you would use 0.1, that would be on the vertical axis here. And then the other value you need to compute is your, for the horizontal axis, is this value RC divided by 1,000. RC would be like a time constant, I guess. Anyway, R is 2,000, again, 2,000 ohms times the 20 microfarads. So it's you just plug in the microfarads, and then divide that by 1,000, and you come out with a value of 40. Okay. So what you do is you look for 40 on the horizontal axis, and then you draw your vertical line up to R divided by RS is 0.1. That's actually the value of one of these curves. So these curves go from 1 all the way down to 0.0. 0.00005, the very top curve. So one of these curves is got a value of 0.1. So here it is. So you draw your vertical dashed line up to the 0.1, the curve that's 0.1, and then you make your horizontal line going over to intercept the vertical axis here, and it comes out at a value of 1.06. Okay, so they say from that, you multiply the value of 1.06 times your RMS transformer secondary voltage of 350 volts. So what they do is they show that here. 350 times 1.06 is 370. So what they're saying is with those values, you're going to only get 370 volts out, okay, out of your power supply. And that's it. Okay, so that's it. So if you want to go for a higher voltage, you're going to have to adjust your components so you can intercept one of these higher curves here, and that will give you when you draw the horizontal line out to the y or the vertical axis, you're going to get a bigger value of factor that you need to multiply your RMS voltage of the secondary by to get your maximum volt. I guess that's maximum RMS voltage anyway, coming out of your secondary. So that's how you would play the game with this thing. So I'm going to stop here, but I'm just showing everybody what it's not so straightforward. If you're doing this from scratch, you really need to go into all this stuff, and the information to do it is very hard to find these days. Because the engineers who design power supplies probably have this stuff is either on computer programs or there's other ways of doing it nowadays. Remember, this came out of the 1984 amateur radio handbook, so in the newer handbooks, they don't even show any of this stuff anymore. So I don't know what they do. But anyway, that's how you kind of go about doing this. And besides, nobody's designing very many power supplies for tube amplifiers anymore, unless you, I guess, you can buy them, but I think the designs for those power supplies have been around for a long time, and that's what they're using. Now, Steve, when you designed your amplifier, What did you do for power supply?
Well, I didn't build the power supply. Initially, I had a Meanwell 2500 watt power supply for it, but it was a bit noisy.
Hmm.
And to show that sometimes good luck follows you, they have a new totally silent power supply. It does what is it, about 2400 watts, but
Wow.
it's fanless, so it's totally quiet. And it cost about $600, and I wasn't, I didn't want to put that out. Well, I just came across a thing on Amazon, a Meanwell ad, and they were advertising that thing for less than $200. Well, it turned out it was a mistake.
Hmm.
Ah,
I ordered it immediately, and the ad disappeared really quickly. I got a thing from Meanwell that said, "We made a mistake, but we're going to live up to it." So they sent me the thing. It came all the way from Taiwan or wherever it was
yep.
made.
Wow.
And it's such a sweet power supply. The problem with any kind of high wattage amp is they're noisy, can be noisy.
Yes. Yes.
And now when my amp put out a bit over 1,000 watts, 1,200 at max, and
Mhm.
I had designed it with a bottom-based computer fan, very large. It forces a lot of air, but slowly, to
Yeah.
cool it off. So the amp itself never made any noise, but now the power supply doesn't make any noise. And
Hmm.
oh, the high noise of the amp before is one of the reasons I didn't use it very often. Right?
Yeah.
It just is. It's fatiguing.
Oh yeah.
And now it doesn't matter where I have the amp or not. There's no sound in my shack. You
Yeah.
know, and oh, I love that. But you're just a few years late. When I decided to go solid state, I sold all of my tubes, all my stuff that I had uh, to somebody in Washington. I know that where did I sell that on? It was either Facebook or Facebook or Marketplace. I don't remember. But I met this guy in the IKEA parking lot in Portland because he was coming down from Washington, and that was midway. And he gave me $150 for the lot and unloaded
Hmm.
my trunk. So sorry, I would have given it to you, but fine.
Oh, and how convenient too. You live 100 feet from me, so
Oh yeah,
yeah.
and you mentioned the 65 watts heat dissipation. That may not sound like much, but if you think of a 60-watt light bulb, how hot it gets,
Yeah.
Yeah.
the old kind, it gets very, very hot, and these tubes also. So
Yeah.
you're going to need a lot of cooling. But although these are relatively low power tubes, so.
That's true.
Oh, the other thing that note in your calculations, there was a big change back in the day when everything was tubed. Power was measured as input power to the amp, not output power.
Right.
And
Right.
with solid state, it's output.
Right.
So, for instance, I had an SB 102. It had two tubes in it, and it was rated at uh, about 150 watts, but that was input power.
Yep.
Hmm.
So the output power, and the FCC rules used to be based on input power, not
Right.
output power, and it it's a lot better now in many ways. But hey, I'm not no longer a couple hundred feet from your house, but a quarter mile. So you walk all the way up and around and down.
I know, unless I jump over the gate.
Yeah,
Well,
yeah,
anyway, yeah, thank you guys for the input. I'm glad that both you and Jeff are on
Yeah.
because I wanted you to see this so you
Yeah.
could, guide me. Now, obviously, I'm being a masochist, A. B, we're talking here linear power supply because with modern switching power supplies, none of this stuff counts anymore.
yeah. They're
So
a
this
lot
is
harder to
strictly for,
build. They're a lot
huh?
harder. They're a lot harder to build.
Yeah.
My very first, back when I was 13, my very first homebrew project was to build a power supply.
Oh, wow.
I didn't have anything to connect it to, but power supplies are pretty easy to build. But I love the glow of the
Oh
tubes,
yeah. Oh yeah.
right? And I was so proud of that thing. And but that was the early days.
Yeah, 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 exactly. So
Those
again,
tubes, they've also you've got to consider the filament current, and the cathode is the filament in the 811.
Yeah.
And so I believe those are 6-volt filaments, and I'm not sure what the average is. Maybe 5. You probably need about a 10 amp filament.
yeah. Well, but
Unless you're lucky enough to catch one of the combined transformers, where they have a
yeah,
filament circuit and they also have the high voltage.
yeah, that's what I would. Yeah, either that or I'm going to go with separate transformers for filament and even for the bias for the high voltage say screen. Oh no, I'm not using those tubes, but well, maybe for the driver tube is a pentode, so it's going to be a screen voltage.
I sent you what I think the model number on that pentode is. I did on the chat. I don't know if you caught that or not.
Oh no, I didn't. Yeah, did you say you think you found it?
Yeah, they did. I sent the chat. I did it specifically to you.
Oh, okay.
And it's what did I say on there? I thought it was a 6Y6 GT.
Yeah,
Oh,
probably,
yes,
yeah,
right
that sounds
then.
right.
Oh, okay.
Thank you.
If it had been just a 6, the 6Y was the key because there's 6 S's, there are various other things, but that may or may not be what it is, but that's probably a good
I
guess.
think it's what it is. Yeah. Anyway, well, thank you all for hanging in there.
Yeah.
Because it's kind of you talk about technical topics. This is pretty technical, but I just thought we never talk about homebrewing, and when I knew that Jeff was on Saturday, Jeff said he was interested in joining the meeting, so I thought, oh, this is perfect because then if he's going to be there, maybe I can talk about this and I can get some feedback, from somebody who knows what they're talking about and see where we go. But again, this is one of those things where it's like, you're kind of crazy for doing it, but then on the other hand, it's kind of fun and it's a challenge of making this work. From some crazy thing I picked up for $25. Not the transformer, but that transmitter or whatever it's supposed to be.
Yeah, that's kind of cool.
Yeah.
But I should warn you, Scott, never assume I know what I'm talking about.
Oh, well, no, it's okay. I'm sure you know a lot more about what you're talking about than what I'm talking about. So, or that when I talk about these things, that I'm just kind of a newbie, but I want to delve into it. I've always liked vacuum tubes, so there you go.
Oh, Scott, this is an admirable project.
Yeah. Well, Jeff, I'm sure we'll be conversing about this. I'll have a lot of questions for you.
Yeah.
As it goes on.
It'll be a fun project. You'll enjoy it.
Yeah. There's others. I'm still into building an STR transceiver as well for get into modern, back up to the year 2025. Because now here we're talking about God, I don't know how many decades ago, but it's kind of the nostalgia is fun for that kind of a deal. And oh, by the way, just before we all go, Jeff, I think you were talking about, or no, was it you? Yeah, you were talking about back in the 60s, to take the test for the general.
Yep.
Well, here is a book.
Oh,
do you have this book?
Yeah. Yes, I do. Yes, I do.
Okay, this was the book for the general.
Right.
Okay, this is how thick it is. This is the kind of stuff. I mean, they talk about, this is the kind of stuff that they were covering.
Yeah, it's a textbook.
Yes.
It is a legit technical textbook.
Yeah.
Ton of information in it.
And I might add, very well written. And they talk about, this is for the general. Go look in the general book today.
Yep.
See if you can find this kind of information. I mean, not that they would talk about tubes.
Right.
But I mean, anything about, say, a variable capacitor here and how it works, they don't show that.
Right.
They don't. And so my students are stumped half the time because going back to the basics is actually the best way to teach this stuff.
Yeah.
If you just kind of introduce something like, here's a variable capacitor,
right,
and you try to show them, it turns and why it turns, but they can't visualize it and they don't understand. Really, if you showed them the picture that I just showed you of a variable, the plate, overlap and all that, of a variable capacitor, then that would make it, it would make sense. Yep. But so I think you got more out of this book if you know, than any other book. Of course, it's outdated now because all it talks about is vacuum tubes. It doesn't talk about
Right,
transistors
right.
at all. But you know, there you go. So,
Yeah.
yeah. So I'm
Amico
glad you
was a
recognize it.
big name back in the day.
Yes, yes, yeah. Anyway, um, yeah. So thank you all for again for listening. It's already 9 o'clock, so it's after 9. So I think it's time to go home. You know.
It
And
was
wow,
it,
what a crowd tonight, huh? We had I don't know if
yeah.
everybody hung in there, but
Oh,
Well, we heard you were doing the technical, Scott, so we thought we'd all show up.
all right.
I haven't been here in a year.
oh,
I
really?
know, I know. I was gonna say we haven't seen you in quite a while.
Well, I got reemployed when I started on a few of these people already heard the story, but an old employer of mine that I retired from in 1992, Unisys, offered me a job, and
Oh,
now I work for the state of New York.
wow.
And what's killed me over the last year isn't the work. The work's been fairly straightforward and easy and interesting. It's the time zone difference.
Yep.
So finally, this is a 3-day weekend, and so I said, I'm not going to be exhausted on Monday evenings. I'm going to show up and listen to Scott.
Well, thank you. Appreciate that, Steve.
I had no idea you were going to be on. So, but
No, I know,
sounds good.
I know. Well, you see, for the new people, this other guy, Mike Shelby, who is out of the country at the moment, he's the one who normally gives the talks.
Yeah.
And his talks are a different approach than mine. They're more like, you know, more relatable, I think, for ham radio. But he's so he was out of town this week, so I said I would, you know, fill in for him, and that's why I'm doing it. But normally it would be Mike. So the next month it'll be Mike.
Okay.
You know.
Interesting job that you did, Scott. Thanks.
Yeah, I like to, you know, throw in the technical stuff because I do the I don't know how many of you are familiar with the technical discussion net on the WA7ABU repeater, the 529 repeater, which is up in Salem, Silverton actually. So every day of the week at 10 o'clock in the morning to 11 o'clock in the morning, we've got the TechNet going, and so I'm a net control for Tuesday morning. So tomorrow morning will be my turn. So we always bring up these kinds of topics on my net. You know, it's you know, because otherwise a lot of times people don't know what to talk about. So I'll introduce a topic. We'll talk about tubes, or we'll talk about transistors, we'll talk about amplifiers, things like that, and then we get a lot of discussion going. And I've got a lot of people on the net, 30 or so checked in, and there's quite a few people that are been around ham radio for a long time, so they know a thing or two about these things, and then they chime in with their knowledge, and it's a lot of fun. So I'm encouraging anybody who wants to join in, if you've got the time, 10 a.m. in the morning on the 529 repeater, no tone required. Please do, you know, check in and at least listen to it, even on Echolink if you have Echolink, and it's quite interesting, you know.
Yeah. Is 5.29, is that what was also known as Snow Peak?
No, I don't think so.
Oh, okay.
It's
okay.
so WA7ABU is Dan. I can't remember his last name. He's the repeater owner.
Yeah, I recognize.
Yeah, he's got actually I think 4 repeaters now. So it's not on the PRA system obviously, but it's a good it's got great coverage. You know, you from Eugene all the way up.
Yeah. Okay.
Huh?
Okay.
Yeah.
I recognize his call sign.
Yeah. Yeah. Anyway, you know, it's a good discussion net. So, and it's one of the few around. I mean, I don't know. We've even got people from Canada that checking out Echolink. You know, they listen to it pretty much a daily basis. So.
Okay.
Yeah.
Well, there's another reason for a dedicated Yagi.
There you go. Yes.
For me.
I tried my 2-meter Yagi.
It
just didn't hit. They're in Saskatchewan and Saskatoon, so it's a little bit far away.
Yeah.
It's not in BC.
I just want a Yagi just for that repeater pointed, and I park it, and I'm done. You know. So okay.
Okay, guys, I don't want to hold you up any further, and thank you for listening again.
Oh,
Scott,
by the way,
this was
Scott,
great. Thanks.
I have a 1500 watt manual antenna tuner that haven't used in a long time, but you could take the guts of that and make a fine pie circuit for your tube amp.
Oh, thank you.
Yep.
All right.
It's just taking up space here.
Okay, I can come over and get it.
Okay.
Okay, yeah. Yeah, very good. And so,
Old
anyway, yeah.
MFJ thing. So.
Okay. Yeah, well, now that MFJ is no longer a company.
Yeah.
It's too bad because that would have been a great place to get transformers.
Yes,
Yeah.
yes, that's true. Well, the guy who was the vendor at Rickreal, we just happened to have that transformer, and I just when he said $25, I thought, I mean, I didn't want to say anything because it's like, okay, I'll take it, but that was a dead. I mean, I don't know where he picked it up from, but it's worth at least $100.
Yeah.
So I figured,
What's the current capacity of that?
it's well, it's 235 volt amps, so it says 1250 volts at 200 milliamps.
Okay.
That's the kind of the nominal thing. So obviously, the other approach I could have taken also, I had these other 807 tubes which take a much smaller voltage on the plate. I could have probably used a full wave rectifier approach and gotten half the voltage. Or sorry, half the voltage that this thing puts out, but a lot more current.
Yeah.
So that was another idea. So anyway, it's not I mean, by standards of transformers for linear supplies for these kinds of amplifiers, it's a pretty small transformer. I think it's kind of on the bottom end. It's 8 pounds, so it's not that big.
Yeah.
Yeah.
Well, it's a $25 transformer, right?
But it was 25. Well, you go online and you look, and you can still buy these things from, say, Mauser or DigiKey, and they're charging upwards of $200. I think.
I was just giving you a hard time.
Yeah, I know. So anyway.
Okay, I got to run.
Yeah.
I got to go to bed. Got to get up early.
Yeah, I know. Me too. Pretty soon.
Okay.
Okay, everybody. Thank you for
Thanks,
nice seeing Anna, NG. Yeah, 7BN over there.
Yep.
And the others, and Anna Lees, who I think is no longer on the group. But anyway, all right, guys. I will see you soon.
Bye.
Bye bye.
Have a good night, everybody.
Bye bye.